This is a weapon. This is also a weapon. Kind of. This is definitely a weapon. It's easy for us humans to tell if something is a weapon. We interact with weapons, or at least the idea of weapons, all the time, and we know one when we see one. Can we get the stupid computers to do the same? I will be exploring my attempt to make this happen in this video presentation of my OR610 project. The dataset I used comes from datasetninja.com. As you can see from this promotional graphic, it comes with thousands of pictures with regions labeled as weapons. The data comes in two parts, the image and the label. The image contains some number of weapons. Each picture has an associated JSON file that contains coordinates for the weapons in the picture, as well as some other administrative data. The pixel coordinates indicated are the corners of a box that contains the weapon. If there are multiple weapons, then there are multiple boxes. The model I chose for this was UNet, which everyone might remember from homework 2, to approach this problem. UNet needs an input image and a mask, and the output is another mask that attempts to replicate the ground truth mask to the best extent possible. That makes data preprocessing fairly straightforward. First, I scaled the images to be squares. Then, I created an equally sized mask image that draws the scaled boxes in white and keeps the rest of the image black. After that, there's nothing left to do but let the model do its thing. The first attempt was somewhat arduous. A UNet with a depth of 5 running on the whole dataset, minus the test set, took about 30 minutes per epoch running on my CPU. For comparison, it would have taken about a day per epoch on Google Colab. Here you can see my training results. Note the intersection over union score I have here at the end of the training period. If we zoom and enhance, we can see that 0.28 is an awful score. What happened? At this point, it's important to talk about some of the issues with the dataset. First, whoever created this made some mistakes when labeling things. For example, get a load of this Marine. The person who made the label probably thought that this was the barrel of a rifle. In reality, this is actually the antenna of the radio the Marine has strapped to them. An understandable error, but an error all the same. Now, for another example, take a close look at this. Close inspection will reveal that this is not a deadly instrument of war, but is actually, in fact, a zester. Kitchen equipment that one could theoretically wield against an adversary, but hardly a weapon by any reasonable definition. This object perplexes me. Is it a cannon? I have no idea, but even if it is, it, again, stretches the definition far beyond the bounds of anything we might consider useful. These are Legos. This is a big army tow truck. As I reviewed the images, aghast at the strange labeling practices, it struck me that the problem I was tackling was overly broad given the size of the data. I decided to refine my dataset to be more narrow. I wanted to get rid of images that were probably more confusing than anything else. In theory, this could help with all of my problems. I could reduce the dataset, making it run faster. I could eliminate bad samples by removing them. And I could refine what the model was looking for to increase its odds of success. So, I got to work. No more Nerf guns. No more swords. No more Legos. No more this thing. No more warships. Just people holding firearms. Since this type of photo constituted the majority of the dataset, there would still be enough to work with. But by limiting the examples of things that weren't obviously weapons, I could hopefully improve the score of my output. So, I spent an hour or two deleting photos from the dataset that didn't meet my criteria. Then I reran the model using the upgraded dataset. It took about 3.5 hours to run, mostly because I decided to do 250 epochs on a depth 7 model. And it was worth it, because my final IOU was... that's not much better than before. What gives? I took a look at some of my example outputs, and they looked okay. I would even say they looked pretty good. Looking more closely at some of the data that I had, it turns out that there was another issue. I could delete pictures and add epochs all day and all night, and it wouldn't change the other problem with the dataset I had selected. the input mask. Consider this rifle. If the ground truth mask is a well-drawn outline of the weapon, then the UNet mask that approximate it like so would give a good IOU score. The guess would be pretty accurate. Since this is how UNet draws, this is all well and good. However, that is not the system we are dealing with here. The mask that the dataset provides is a massive box, so a really good UNet guess actually gives a terrible IOU score. In addition, the giant box contains a ton of non-weapon information. These white space zones are just as much a part of the answer as the actual weapon is, making it harder for UNet to learn what's going on. Take this example output I had near the beginning of my testing. The image clearly depicts a man holding a machine gun. If we display the mask that the dataset provides, we can see that it certainly contains that weapon, but it also contains a whole lot of other stuff. If we now look at the mask that my model produced, while not perfect, it's probably a lot more accurate than what the ground truth actually tells us. So what that means is my model can actually be running a lot better than the IOU score would tell us. But without good training masks, it's going to be very difficult to really lock in a very good IOU score. Unlike the weird weapons classification issue, this was not something I could easily resolve without just getting a new dataset. However, I think there is a valuable lesson or two to be learned here. First, learning tasks like this are garbage in, garbage out. While networks like this can be very powerful, they can still be hampered significantly by incomplete or lazy data. The data matters. The labels matter. If you don't understand it or if you give it weak information, then your outputs will suffer. Accuracy will be lost. All things considered, I'm actually pretty happy about how well my model did. If I find myself with a month of free time on my hands, I may go through the dataset and create accurate masks and rerun my model to see what effect it has. Until then, thank you for watching.